Okay, we are at the very start of chapter 3, and so we're kind of done with limits, but not really. So we're going to start using limits to help us find things. So we're starting with section 3.1, which is called Introducing the Derivative, which I know you've probably never heard that word before, especially in a math class. So it's brand new, but we're going to be using a derivative for so many things this semester. Derivatives are probably what we're going to spend about 75% of the course working with. And then the second half of the course, we're just going to do the opposite of a derivative, which we call an antiderivative. So before we get to what a derivative actually is, let's just first look at some lines and look at what we call rates of change. So we're just going to draw some pictures. Let me go ahead and just draw a little XY axis, and then we're going to just draw an exaggerated cubic function. And so the first thing we're going to look at are tangent lines, okay? And we're going to call a tangent line, that's going to be a line that intersects a curve. How many times? So how many times can a line intersect a function? And the answer would be twice, because if it's more than 2 times, it's not necessarily that function. So we want it on that given interval. So it's going to intersect a curve once on a given interval. Okay. So basically what we want to do, and if you have another color, go ahead and use that now. What we're going to do is we're going to pick out a point, and I want you to draw the line tangent to the function at that point. That means that when you cross that point, I don't want you to go through the function anywhere else on that interval. So what we want to do is we want to basically skim that function so that that tangent line hits it at one and only one point. And we could pick the point to be wherever we want. We could pick the point to be right here, and then you have your tangent line. Now the reason we say on a given interval is because technically that tangent line will hit the function over there. But I'm not worried about that. All I'm doing is I'm looking in this kind of region right here, drawing the tangent line. And so what that means is we wanted to hit the curve at one and only one point. Let's pick one more point up here. Draw your tangent line. Okay. And then so I'm going to go ahead and show you a video of, not video, but an animation of what this could also look like. So we have a function here. You can see the purple point there. And then what we're going to do is we're going to basically move this point. And so whenever I move that point, it's also going to move the tangent line. Now I want you to start thinking, what's happening with this line? One thing I notice right now is that the line is going down. The line is decreasing. Okay, and the line, and I'm going to move the point. The line is still going down. It's decreasing. The line is still, oh, whoops, hold on. The line is still decreasing, but it's getting less steep as we go on. So it's going to be decreasing. It's still decreasing. And then all of a sudden, I'm constant. My line is horizontal. But then my line starts increasing again. Or not increasing, my line starts going up. So it has a positive slope. So why is that? Like, what's the rule of thumb here? So let's draw 2 just like kind of basic mini parabolas over here. And we're going to pick out a couple points on here. So for this first one, I want you to draw the tangent line. Okay? Tell me something about that line. And again, if we were in class, we'd be talking about it. One thing you should notice is that this line is going up. It has a positive slope. Okay? This line has a positive slope. Whoop, that's not how you spell slope. Verse, if we put the point over here and drew a line, a tangent line, this line has a negative slope. Okay, but why? Why would one have a positive slope versus one have a negative slope? And hopefully you can already see it's about where the graph is going. On this first half of the graph, my function is increasing. So that's why the slopes are all positive. The second that my function stops increasing and starts decreasing, the slope of that function becomes negative. Positive slope because f is increasing, and negative slope because f is decreasing. So where does it stop from increasing to decreasing? Okay, and hopefully you can see it's like right here. So what would we call that point in terms of that function? Okay, the point where we stop going increasing to decreasing, that's going to be called the maximum of my function f. And what's the slope at the very top? Well, if I were to draw a horizontal line, what's the slope of a horizontal line? And hopefully you can remember the slope is 0. Well, that makes sense. If you have to go from positive to negative, you're going to have to cross 0. And so even looking at the other parabola, this minimum of f is where we also have a slope of 0. Okay, I see on the right side that f is increasing. Well, what we're going to start using all the time is that when f is increasing, its slope is positive. It's greater than 0. And over here, if f is decreasing, its slope is negative, less than 0. And we're going to start using that kind of stuff all the time. And you may think, well, why? Well, again, we'll get there. We're just trying to get the basics down. Okay, so now what happens if I draw pretty much the exact same cubic function that I drew the first time, but now I want to pick 2 points for this line to go through? And we draw our line. Is that a tangent line anymore? Well, no, it goes through 2 points on that given interval. It's not kind of skimming the function like the tangent line did. So we're going to call that a secant line. Okay, for the secant line, that's going to be a line that intersects a curve or a function twice or 2 times on a given interval. Okay. Now, why would we need to use secant lines? Well, if you can remember, and actually let's go ahead and draw an exaggerated picture here so we can start to mark on it. Okay, let me go ahead and draw just an upside down parabola. Let's pick point A, point B. So let's actually call that x value is A and that x value is B. So if I go through those 2 points with a line, and I draw a secant line, and I said, find the slope. Do we know how to find this actual slope of that line? I can already see that the slope is positive because the line is going up, but what is the slope? What's the number? And hopefully you remember back from Algebra 1 that we have a slope formula. It was the y2 minus y1 over x2 minus x1. Okay, but let's use it in terms of our x values A and B. So if the x value is A, the y value is going to be f of A, and this y value up here is going to be f of B. So now let's go ahead and do the slope formula. The slope of this line is y2 minus y1 all over x2 minus x1. And we can find the slope of that line. I mean, as long as we had a certain number of x values, it would be no problem. Okay? And that's what we're going to call our average rate of change. So, our first definition, we're going to say AROC, the average rate of change. So, the only time I'll probably write it out. The average rate of change, or AROC as we're going to call it a lot of times, is the slope of the secant line. And we're just going to go ahead and rewrite that slope formula that we just found above. Okay, so the slope is the f of B minus f of A all over B minus A. Okay, now here's where we run into a little bit of a problem. So you do not need to turn back, but I'm going to. If I said find the slope, let me call that A. If I said find the slope of this line here that I'm going to highlight in purple, well, it's already in purple, if that I'm going to highlight in blue, how would you find the slope of that line? If you only know one point on that line, how are you going to find the slope of it? Because we've only ever found the slope of lines with 2 points. And so eventually what we need to be able to find the slope of the line with just 1 point on it. So we're going to look at another animation. Okay. And so right now I see a secant line. And basically, if I want to turn this secant line into a tangent line, how would I do that? And there's a lot of different things you could do. But what I would think of to do is let's move this green point closer. Whoops. Let's move this green point here closer. Is it still secant? Well, yeah, it's still going through 2 points. So I'm going to keep going closer and closer and closer and closer. Oh, until I made it. Until I've turned those 2 points into 1. So when have we done that in calculus? When have we done something that we said, hey, as you go towards this other thing, find the slope? Or as you go closer and closer and closer. And hopefully you can remember, well, that's what limits were. Limits were as x approached something. So we're going to do the same thing here. Okay, so what we're going to do is, I want to put a little side note here. Okay, I can choose whichever variables I want. So let's make the same. Let's do an upside down parabola this time. Let's call this one A and this one X. Okay, find the slope of that line now. Well, that would just be f of x minus f of a all over x minus a. Now, we're going to use this one the most, so box it in, but we're going to use the second one to help us with this limit part. So what we want to happen is we want x to get closer and closer and closer to a. So that way f of x will get closer and closer and closer to f of a. And so what we're going to do is we're going to write a limit statement in front of this one. We want our limit to be as what approaches what. And the limit we want is we want x to approach a for that slope. And that's how you're going to find the slope of the tangent line, because we're going to move that second point so much closer that it's basically going to converge to 1 point. Okay, so let's go ahead and write down our second definition. The definition, okay, for IROC. Well, this is one definition. We're going to learn a couple. Okay. The instantaneous rate of change, or IROC, is called the derivative. Derivative. So that's another word for the derivative. Okay, so what we're going to do is to find the instantaneous rate of change, or the derivative, at the point. So we're going to pick the x value to be a, which makes the y value f of a. We're going to use that same slope formula with the f of x minus f of a all over x. We're going to use that same slope, but now we're going to put the limit statement out front of the f of x minus f of a all over x minus a. Notice when you have 2 points, you do the slope formula for the secant. When you have 1 point at 1 point, then we have to use this slope formula. Okay. The other thing we're just going to kind of throw in here, and we're not going to use this one yet, but basically once you find the slope of the line, we're going to be able to write the equation of the line. So the equation of the tangent line, okay, You can use y equals mx plus b. However, we're probably not going to use that one very much. We're going to use what we call point slope form. Now, why would we use that form? Well, because look at what you have. You're going to be given a point and you're going to be finding the slope. So you're going to use both of those. And point slope form is y minus the y value, which is the slope, x minus the x value in the point. Or if you want to write it with our a's and b's that we've been finding, y minus f of a equals some slope x minus a. Okay, and that's what we're probably going to use the most because we don't have to clean it up on the free response. Now, that was a lot of introduction. So let's actually get to an example now. Let's try a problem. All right, example 1. We're going to let f of x equal negative 16x squared plus 96x. And I'm going to give you the point. And if I sub in 1, if I plugged 1 into this function, negative 16 plus 96, that will give me the y value of 80. So if I ever just give you the x value, just sub x in to find y. All right, and that point on the curve. Part A, because we're going to have multiple parts. Part A, find the slope of the line tangent to F at point P. Okay. Now, if I would have just given you 2 points, you would have done the slope formula, y2 minus y1 over x2 minus x1. But it's impossible to do the slope formula if we only have 1 point, unless we put a limit statement out front. So let's go ahead and rewrite our limit statement. So underline slope, underline slope. Okay, we're going to find the slope using this limit formula. Okay, this is how you find the slope at a point, for right now. So let's figure out what all the missing pieces are. You should be able to replace a, f of a, we already said a, and f of x. The only thing left in there is x. So let's start figuring out what everything is. Your a value is your x value. So this is your a, which makes this your f of a. Whoops, what did I just do? Your f of a. So a is 1, and f of a is 80. Okay, we already know what f of x is. That's the original equation that they gave us. Negative 16x squared plus 96x. Okay, and so now what we're going to do is we're just going to replace everything. So this is not as x approaches a anymore. I'm going to say the limit as x approaches 1 of my function, negative 16x squared plus 96x. So that was your f of x. Hold on, let me mark it up because you'll want to see this marked up just for later. So this is your f of x minus, now I need to put my f of a in there. My f of a is 80. F of a all over x minus a, your x value. Okay, well now guys, it's just a limit. And we've been solving limits for probably 3-4 weeks at this point. So you're just going to treat this like any other limit. What's the first step in any limit? Well, you sub the number in. So I'm going to replace every x I see with 1. So negative 16 plus 96 minus 80 all over 1 minus 1. Let's see, the top, surprise, surprise, the top is 0, the bottom 0. This is indeterminate. Do more work. Do something else. So I see quadratic. Let's see if we can factor and cancel. Factor and cancel. Okay, so let's go ahead and try to factor the top. Let's take a negative 16 out. Limit x approaches 1. Negative 16, we get x squared minus, I think that's 6. And then that's going to be plus, I believe, 5. Now again, you better get the top to factor as an x minus 1. So limit x approaches 1 of negative 16, x minus 1, x minus 5 it looks like, all over x minus 1. All right, I'm going to factor, cancel, try my limit again. So I'm going to replace x with 1. We get negative 16, 1 minus 5. Negative 16 times negative 4 is positive 64. What is that? That's the slope. That's the slope of the line tangent. Okay. Now, a lot of times, if I want the slope, I might also want the equation of the whole line. So let's think about what we're doing here. We have, whoops, what did I just do? There we go. We have a parabola that's opening down because this a is negative. So I have a parabola that's opening down, going through the point 1, 80. So again, somewhere up there. Let's just draw a random parabola. And we have this point. Now what we just found was the slope of the tangent line. And so if I were to draw the tangent line, that does have a pretty steep slope. So now I want the whole equation for that line. Okay, part B. Find the equation of the line tangent to F at the point 1, 80. All right, so when we write a tangent line, we're going to use the point slope format. So those are the two things that you need. You need a point. Well, we already know the point. The point is 1, 80. And I also need a slope. And we just found the slope to be positive 64. So we're going to go ahead and use our point slope form. I'm going to go ahead and rewrite the basic step. It's y minus y1 equals mx minus x1. Now what you're going to do is replace everything. We already know our m over here. This is going to be my x1. This is going to be my y1. Y minus the y value equals 64. X minus the x value. And the x value here was 1. And honestly, on the free response, you can just leave that. A lot of people like to add 80 to the other side. I wouldn't distribute the 64 because it's nice to see it all kind of in its own spot. Just from looking at this, I can see what your slope is, what your point is. So I wouldn't really distribute and clean it up unless they do on multiple choice. But this is just where you would stop. You wouldn't even have to really clean it up anymore. Okay. All right. We definitely need to try another problem similar to that. So I might skip ahead in the notes to example 2 on that one. Example 2. All right. I want you to find the slope and the equation of the line tangent to this function, f of x equals 1 over 2x minus 3 at x equals negative 3. So, first of all, what did I do differently here? Well, I see two things. One, I gave you a rational function. So I gave you an equation that was a fraction. The second thing is I didn't give you the whole point. I just gave you the x value. So when you see that, pretty much right away, what you're going to do is you're going to sub x in to find the y value. Let's find f of negative 3. So 1 over 2 times negative 3 minus 3. That's going to be negative 6 minus 3, so negative 1/9. That's your f of a value. All right, let's go ahead and write down how we get the slope first, because we already have the point. Now we just need the slope. So for my slope, limit x approaches a, f of x minus f of a all over x minus a. And now let's start replacing everything. We know that a is negative 3, so we have limit x approaches negative 3. Let's go ahead and replace my f of x equation. F of x minus f of a all over x minus a. And we already know x, so x minus negative 3 would be x plus 3. Now, I don't really like the minus negative at the top, but I wanted you to see that here's your f of x, here's your f of a, all over x minus a. And so I would write that in another color so it stands out to you, because this can be really challenging for a lot of students. I know the IU dual credit final, they always have them do something with the limit. They call this the limit definition of the derivative. They always have something with this. All right, so I'm just going to rewrite this so it looks a little bit cleaner. But guys, it's a limit. We should already know how to solve limits. This should be nothing new for us at this point. Plus 1/9 all over x plus 3. So the first thing we do with the limit, we know we sub our number in. So I'm going to sub in negative 3. I know the first one is negative 1/9. This one's positive 1/9 all over negative 3 plus 3. And it's 0 over 0. Indeterminate. Do more work. This is not a factor and cancel kind of problem. What do we do for this one, though? For me, when I see a fraction inside a fraction, I need to multiply by the least common denominator, LCD. So let's go ahead and find that LCD. Look at all three denominators. And remember, this one's over 1. So one denominator is 2x minus 3. One denominator is 9. And the third denominator at the bottom is 1. So I'm not worried about that one. So you're going to multiply every single piece by 9, 2x minus 3. So I'm actually going to rewrite the limit statement so it looks cleaner, and I'm going to leave a little room. But if you don't want to rewrite it, that's fine. Limit x approaches negative 3. 1 over 2x minus 3. I'm going to leave a little space. Plus 1/9. Leave a little space. All over x plus 3. And you can put the over 1. I might actually put that in parentheses. All right, every single piece gets multiplied by your LCD. Everything gets multiplied by 9, 2x minus 3. 9, 2x minus 3. So times 9, 2x minus 3. Times 9, 2x minus 3. Times 9, 2x minus 3. Okay, so if you did your job, all the fractions in the top should cancel out. So cancel. 1 times 9 is 9. Limit x approaches negative 3. We get 9. The 9s cancel, and I don't really need to distribute a plus 1, but just be careful there. Plus 2x minus 3 all over, and I'm just going to reorder the denominator a little bit. Now, do not cancel those 9s and that 2x minus 3. You have to clean the top up, so please don't scare me and start to cancel things that can't be canceled, because that would get me a little upset. Okay, I'm going to go to the next page and rewrite it so that way we can see it better. Paste. Okay, let's clean the top up. 9 minus 3 is 6, so 2x plus 6. I already see what's going to happen. You might be getting close. We're just kind of reworking this. I know something's supposed to cancel, though. If it was indeterminate, something's supposed to cancel. So I'm going to factor a 2 out of the top. And then hopefully you can see what's going to happen top to bottom. And I see it. X plus 3's cancel. I'm going to try my limit again by subbing in negative 3. So 2 over 9. 2 times negative 3 is negative 6 minus 3. So that's going to be negative 2 over 81, because this one is a negative 9 here. Now, what's that number again? That's the slope of the tangent line. That's my slope. And that's part of what they asked for, but they also want the whole equation. So, for my equation of my tangent line, I'm going to first write my basic format, and you need to do this until you have this so memorized that you don't even need it anymore. Y minus, what was my y value of my point again? I have to turn back. My y value we found was negative 1/9. So y minus negative 1/9 equals my slope, which I just found, x minus the x value. The x value was negative 3. So x minus negative 3. And you may stop there. I like to get y by itself, but that's just my opinion. So I'm going to subtract 1/9 to the other side. Negative 2 over 81, x plus 3 minus 1/9. And that's my equation.